Hi, I'm going to be talking about the measurement postulate of quantum mechanics and whether it throws up any interesting implications about the underlying physical theory that we're actually learning here in quantum mechanics. Um, so we start with the postulates of quantum mechanics. It's actually built from a rather small set of pretty courageous and brilliant postulates, and in many respects the bare bones of it have some pretty strong analogues from classical mechanics. You know, in classical mechanics we've got a state with our positions and momentums and the sort of state's space, the phase space, you know, spanned by all of the possible positions and momentums, and often our trajectories through phase space are constrained by some energy surface defined by the energy of the particle. And in quantum mechanics we've got a similar kind of vibe. We've got our state, it's spanned by we've got a state space, the Hilbert space, and it's spanned by the energy eigenstates of the Hamiltonian of the particle. So yeah, obviously we've got pretty similar descriptions of state. What about some dynamics? In classical mechanics we've got our Hamiltonian mechanics, just a couple of cute little first order PDEs, something like that. And of course the equation that I'm sure we're all very sick of seeing, the Schrödinger equation, another first order partial differential equation. We have a lot of similarities, and back in the day, you know, you had these dudes with funny hair, mainly white fellas, and they were going, great, that's it, we're done. But as white fellas often are, they were foolish to think that, and apart from discovering all of this nonsense, we quantum mechanics people said, 1 second, we need to add a little bit more onto the formalism here to make it agree with the experiments. And this is where the measurement postulate comes in. It says, well, if we've got some operator and we can expand it into its spectral decomposition of all of its eigenstates, and we've got some state that we can describe as a superposition of those eigenstates, then if we ever go ahead and decide to measure this observable, we will collapse this superposition to a definite value. We're going to go from a nice smooth wave function that evolves according to the Schrödinger equation and exists within this state space. We've got a very kind of physical feeling to that, and then it just snaps to one of these with a probability associated with this, not with that, with this, mod squared of that. And this is the measurement postulate. It says if we make a measurement, it's game over for the Schrödinger equation. This nice, smooth, physical, evolving wave gets violently pushed. So we've come quite a long way from our classical roots here, but maybe that's alright. Nature doesn't have to care about our medium-sized, medium-speed, anthropocentric intuitions about how it works. But then again, you know, classical mechanics and the physical approach that led to it was built on looking at data and trying to come up with a plausible way of talking about the underlying reality from which the phenomenon we observe has emerged. So what physically is happening in this measurement process? It's kind of an unanswered question. We just postulate it, because it's what we need to fit our experiments, but I don't know, who gets to make a measurement? What is a measurement? When does it happen? Does it happen if we glance at the particle, or do we have to look at it for a second? Or, you know, can I make a measurement but my friend Jim can't? Can a rock make a measurement? There's a lot of unanswered questions about how this snapping process goes along. How fast does it happen? Does it happen at faster than the speed of light, for example? We've got a lot of unanswered problems, and these problems and the various philosophical conundrums that stem from them are known collectively as the measurement problem. And if we take them all seriously, we come to the rather disturbing conclusion that we've been lied to by our trusted lecturers for the past 3 years. So how might one reconsider quantum mechanics so as to avoid the violent intervention in what is otherwise a very physical and coherent and mathematically elegant picture? Well, to do that, we're going to turn to a well-loved experiment in the course, the Stern-Gerlach experiment. Right, so here we have the setup for the Stern-Gerlach experiment. So it was first performed with silver atoms, but we're just going to send in some electrons today, if that's okay by you. Our electrons can be represented as a superposition of some spin up electrons, where up is the axis of the magnetic field here, and also we've got a component in the spin down direction. So the thing that they observed is that if we shoot a spin up electron, well, if we shoot an electron out, it doesn't really matter what arbitrary superposition it's in. It seems that in the spin up case, it's just gonna definitely go to here. We've got, this is the midline. It's going to be deflected in this very specific trajectory. And similarly, we can shoot an electron through and it might go up here. This would be the spin down electron. And this was very interesting, and basically it just illustrates our measurement postulate. We've got, you know, a superposition in this area, and then in this area it seems like the superposition has snapped. We've had a measurement occur, but where? Here? Or here where it splits, maybe? Or somewhere in the middle? Does it happen suddenly or gradually? What if the apparatus is a bit chunky and it, you know, turns off halfway through? What happens? We've got no physical way of talking about what's going on, and we're physicists. We demand to know, how does the electron behave as it makes its way through here? How do we describe it? And yeah, essentially the measurement postulate is giving us a bit of a raw deal in terms of actually being able to describe physically what goes on the whole way through. So we'd like to know more. So if all I've done is confuse you about whether we've been told porcupines for our whole quantum mechanical education, then let me propose a tentative and entertaining way of thinking about the physical evolution of our electron as it passes through the Stern-Gerlach magnet. We're first going to have to take a bit of a deep dive into a fast approaching topic, which is entanglement. We just want to consider an electron in some superposition moving through space, and it comes across a photon that it interacts with. Now the electron's got some wave function, and surely so does the photon. And when they interact, the interaction is going to be different based on whether the up state of the spin or the down state of the spin is kind of regarded by the photon. The photon might pop off in this direction if it's in the down state, and it might go off in this direction if it's in the up state. And similarly, the electron's gonna, have some motion based on whether the interaction goes one way or the other, based on its superposition of up and down spin states. So you might think, well, does a measurement happen in this case? Like, is this interaction gonna cause the electron's wave function to collapse down into one and the photon's wave function to collapse down into one? And it turns out that apparently photons just don't cut the mustard as an observing thing. It's another weird thing about the measurement postulate. It kind of like posits some macroscopic observable object that can influence the wave function in that way, but doesn't happen when you have these interacting single particle systems. What goes on actually is that a new wave function is defined that's kind of like the wave function of the electron and the wave function of the photon. It's a new combined composite system, and all of these different contingencies of the spin up and the electron scattering the photon off this way is superposed with the possibility of the electron spin being down and the photon scattering off in a different direction. All of these different possible evolutions get combined into this composite wave function. And indeed, if you don't contain your system, this entanglement can spread a bit like a virus. These scattered photons affect other molecules around, and the environment takes on, lots and lots and lots and lots and lots of different component wave functions, such that the state of the thing can be entangled with lots of different objects around it. So with that picture in mind, I'd like to move on to a new point. So we're back at the Stern-Gerlach experiment, and we want to now talk about how an electron might move through this space with more of an entanglement regime in mind. We can think of the magnetic field here as a haze, a hailstorm of photons just pelting down from one terminal to the other, carrying the momentum and force that characterizes the field. And we can also think about this room as being full of molecules of air, and the structures, all of the electrons relating each of the structures in the solid. And we've got this measurement apparatus here, this screen that feeds information about what it detects on its surface into this computer, and we've got a scientist here sitting at the screen. This is all ready to go. So we send our electron through, and what begins to happen is that as it interacts with these photons, we get this entanglement that we were talking about. A photon might consider the spin down case, or it might consider the spin up case, and the photon and the electron become entangled, and a new wave function involving both of their wave functions will encapsulate all of those different options. And then the red photon here that was at spin up sort of thing will hit an electron in the gas and in the room, and this entanglement will continue as the light bounces around, and the results of the initial and all of the measurements are to do with whether the electron's spin up case was considered by the initial interaction, or whether the spin down case was. And essentially what we have is, eventually, as all of the light bounces around the room and the electron makes its way all the way across here and, lands on the screen, we have this new composite object that is described using a single wave function, this entangled room of particles. And the wave function, it's in a superposition of, among all of the other wave functions, it's got this electron's wave function, so it's got some spin up part to it, and then all of the other things that come from that. And it's also got some component that's got all of the interactions, but it might have been spinned down instead. So we've kind of got this dual thing, and when that, when all of the particles in the measurement device become entangled and this sort of heads down into the computer, the scientist becomes entangled as well, and we've got the scientist gets joined into this new composite wave function here, and essentially, we've kind of gone and branched off into two new wave functions. One, this is our sort of branch that takes the Z, the spin up state, and all of the other, and this one, has got some consideration of the spin down components. And these two parts of the wave function of the whole scientist electron room experiment thing are just two branches of the entangled wave function of the entire system. And really what we've got on both of these branches are the wave functions that describe an entire room. In a lot of ways they are like rooms in themselves. It's just that they are separate parts of this composite wave function. It's almost as though the wave function of the entire room has split into two kind of separate realities, where in one, the scientists are sitting there and they've measured spin up. But there's an equally clever and equally real scientist on this branch that says spin down. And it's the sureness of that position, because you are literally on your own branch over here, that leads to things like the measurement postulate. This person and any scientist in this world, as it continues to evolve, is going to say, well, I've got some electron state that was initially in a superposition. It's got some wave function that's a superposition, and now it's in spin down. It's snapped to this eigenstate. And so that's just obviously a pretty wild proposition, but it was made by a guy called Hugh Everett. Probably should have looked up the spelling. Back in the day, it was in the, I don't actually know what decade, maybe like the 40s or something like that. And it's called the Everettian many worlds interpretation. So just to take stock, it's a theory that gets away from this discontinuous snapping of the wave function evolving through space, and then a measurement happens and it snaps to one location. Now we have the wave function evolving steadily, and that's it. That's basically the whole story. It interacts with other particles. The wave functions and Hilbert spaces of the composite system of those interacting particles become entangled, and when the entanglement seeps out into the whole environment, you essentially get the environment, the wave function, branching off into these two lanes, where on both sides people would see and postulate something like the measurement postulate, but in fact it is just because they are on one and not the other branch of this evolving system. So yeah, I'd encourage you to have a Google of this if you're at all interested, and if you think it's completely wacky, then that's probably fair as well. So yeah, thanks for listening to my presentation.